Hello and welcome back. In the previous video, we discussed something called electromagnetic induction, which is this phenomenon where a voltage is induced inside a coil whenever the magnetic flux through the coil changes. And one important thing to understand about electromagnetic induction is that electromagnetic induction does not give you something for nothing. In other words, energy is still going to be conserved. So for example, some of you might be thinking to yourself, well, if I have this coil over here, and it starts out in a region where there's no magnetic field, and it's moving to the right with some speed, v, and then it enters into a region with a magnetic field, then what's going to happen is that as this coil moves into the magnetic field, there will be a voltage induced inside this coil. So I'm just going to get something for nothing. I'm going to get this electrostatic potential energy for free whenever this coil moves into the magnetic field. And it turns out that that's not really the case. And the reason is that whenever a coil moves into a region with a magnetic field, the current that's induced inside the coil will interact with the magnetic field to create a magnetic force which opposes the motion of the coil. So in this example down here, I have this coil which, let's say it started out over here towards the left where there was no magnetic field, and the coil is moving towards the right. So as the coil moves towards the right, it's going to enter a region with a magnetic field which is pointing into the screen. So that means the magnetic flux through this coil that points into the screen is increasing. Now remember, Lenz's law tells us that the current that's induced inside a coil will tend to create magnetic fields which oppose the change in the magnetic flux through the coil. So since we have an increasing magnetic flux which points into the screen, the coil will tend to create a magnetic field which points out of the screen to try to cancel out that increasing magnetic flux into the screen. And remember that when you have a coil, if you curl the fingers on your right hand in the direction that the current flows through the coil, then your thumb is going to point in the direction of the magnetic field. So if we want a magnetic field which points away from the screen, if you point the thumb on your right hand away from the screen, you can see that your fingers are going to curl around in a counterclockwise direction. So that's what I have indicated by these arrows here. So the current flowing through this coil is flowing in this counterclockwise direction. And as I mentioned before, the induced current inside the coil will interact with the magnetic field to create a magnetic force which opposes the motion of the coil. So we can see that over here on the right side of the coil, we have this current which is flowing towards the top of the screen. Now if I apply the right-hand rule to find the direction of the magnetic force exerted on that wire, we'll see that that force is going to point towards the left. So again, applying the right-hand rule, if I point my fingers in the direction that the current is flowing, so if I point the fingers on my right hand towards the top of the screen, and then I orient my right hand so that when I curl my fingers, they're going to point in the direction of the magnetic field, which points into the screen, then I can see that my thumb is going to point towards the left side of the screen. So we can see that the magnetic force that's exerted on this right segment of this coil is going to point towards the left side of the screen. Now one thing that I want to point out about this is that this magnetic force is only exerted on the right side of the coil because the left side of the coil is not inside the magnetic field. So for example, at some time later, if this coil continues to move towards the right, eventually the coil is going to be completely in the magnetic field. So we'll have something that's going to look like this. We're going to have this coil that's completely inside the magnetic field. And so the current might still be moving through it in the same direction. And the point is that if I calculate the magnetic force that's exerted on this coil now, I'm going to see that it's going to cancel out because I'm going to have this magnetic force on the right side of the wire, which is going to point towards the left, and then I'm going to have this magnetic force on the left side of the wire, which is going to point towards the right. So it turns out that there's only a net magnetic force on a coil whenever the magnetic flux through the coil is changing. So if the coil is moving around in an area where the magnetic flux is not changing, then there will be no net magnetic force acting on the coil. However, if you try to move this coil into or out of the magnetic field so that the magnetic flux through the coil changes, there will be a net magnetic force exerted on that coil which is going to oppose that motion of the coil. It's going to try to keep the coil wherever it was so the magnetic flux remains the same. And so what this means is that whenever you try to create an induced voltage inside a coil by changing the magnetic flux through the coil, you're always going to have to do work against this magnetic force. So for example, if you have a power plant or something like that, you're always going to have to do work against the magnetic force which is created by the interaction between the induced current and the magnetic field. So let's take a look at a more quantitative example so we can see that energy is actually going to be conserved. And in this example, we're going to be looking at a gravity-powered circuit. So we're going to have this rod which is completing the circuit, and the rod is going to be falling down. And as the rod falls down, the magnetic flux through the circuit is going to be changing, and that'll induce a voltage. So here I tell you we've got this conducting rod, and it's connected to these two vertical tracks, and it's sliding down the tracks at a speed of 4 meters per second. And in this area there's a magnetic field of 0.5 Tesla which points perpendicular to the track. And the rod has a length of 1.3 meters, and there is a resistance connecting the two tracks of 0.75 ohms, and all of the other resistances in the problem are negligible. And there are three parts to this question. The first part asks us to find the mass of this rod which is powering the circuit. The second part asks us to determine the change in the gravitational potential energy during the first 0.2 seconds as this rod falls down. And then part C asks us to determine how much energy was lost inside that resistor. So here I have a picture kind of illustrating this idea. So we have this wire that comes up here, passes through a resistor, and then comes down. And then this rod is connecting these two wires together. So this rod with this wire up here is going to enclose an area. So this is what's creating our coil. And of course, as this rod falls down, so there's this gravitational force which is pushing down on this rod, and as this rod falls down, the magnetic flux through this whole coil here is going to be changing. So let's just go ahead and apply Lenz's law to determine the direction of the current flowing through this. So because the magnetic field is pointing out of the screen, and as this rod falls, we're going to be increasing the magnetic flux that points out of the screen, the coil is going to tend to create a magnetic field which points into the screen to try to cancel some of that increasing magnetic flux out of the screen. So again, remember, the direction of the magnetic field that's created by a coil is found through this right-hand rule. So if you curl your fingers in the direction that the current flows, your thumb will point in the direction of the magnetic field. Here we want a magnetic field that points into the screen. So if I point the thumb on my right hand into the screen, I can see that the fingers on my hand are going to curl around in a clockwise direction. So the current flowing through the circuit is going to flow around in this clockwise direction. And what that means is that down here, where this rod is, the magnetic force that will be exerted on this rod is going to point upwards. So we can see that by, again, applying the right-hand rule. So the current here is pointing towards the left side of the screen. So if I orient my hands so that my fingers point towards the left side of the screen, and then I rotate my fingers into the direction of the magnetic field, which points out of the screen, then I see my thumb is going to point towards the top of the screen. So this magnetic force is going to point towards the top of the screen. So it's going to oppose the motion of this rod as it's falling down, because it's trying to keep the magnetic flux in this coil constant. And so the first part of this problem is really just realizing that this magnetic force has to be equal to the gravitational force, and we can then use that to calculate the mass of this rod. So I'm going to need a little bit of extra room to work through this problem, so let me go ahead and open up a blank screen. So once again, I've written down the information that was given to us in this problem, and then I've drawn another picture of the problem that we're looking at. And the basic idea behind the first part of this problem, where we try to find the mass of this rod, is that because this rod is falling down at a constant speed of 4 meters per second, this tells us that the magnetic force that's opposing the motion of this rod has to be perfectly canceling that gravitational force, since the rod's moving at a constant speed. So right away we can say that the gravitational force is going to be equal to the magnetic force. So mg is equal to, and remember the magnetic force exerted on a rod is equal to IBL times sine of the angle between the current and the magnetic field. However, if we look over here, we can see the current is flowing towards the left and the magnetic field is coming out of the screen. So this angle theta is going to be 90 degrees, and sine of 90 degrees is 1. So we have that mg is equal to IBL, or the mass of the rod is equal to the current flowing through the circuit times the magnetic field and the length of the rod divided by G. However, we don't really know the current that's flowing through this circuit. We can figure out the current flowing through the circuit, though, by using the formula for electromagnetic induction. So as this rod slides down, the magnetic flux through this whole thing is changing, and that's inducing a current. And we can calculate that current because we can calculate the voltage that's induced in this circuit, and we know the resistance of the circuit, so we can use this with Ohm's law to calculate the current that's flowing through it. So let me go ahead over here to the left and calculate this. So the idea is that the voltage that's induced inside the coil, remember, is equal to N times the rate that the magnetic flux is changing. And in this case, N is just equal to 1, because there's only one turn around this coil. And here, remember, the magnetic flux is equal to BA times cosine of the angle between the direction that's perpendicular to the coil and the magnetic field. Now hopefully you can see that because this coil is within the plane of the paper, the direction that's perpendicular to this coil points out of the screen. And the magnetic field also points out of the screen. So this angle phi here is equal to 0, and cosine of 0 degrees is 1. So the magnetic flux is just equal to the magnetic field times the area that's enclosed by this coil. But of course my area is always changing, because as this coil falls down, this area is going to be increasing. So the rate that the magnetic flux changes is just equal to the strength of the magnetic field times the rate that the area enclosed by this coil is changing. And the area enclosed by the coil is going to be equal to the length of the rod times how far it's moved. So this rate that the area is changed is equal to the length of the rod times the velocity that the rod is traveling at. So the EMF induced is going to be equal to BLV. And in fact, this is the same formula as the motional EMF. This is the same voltage that would exist, or that would arise between the two ends of a rod if the rod is just moving inside a magnetic field. And we talked about that in the previous video as well. So this is the EMF that's induced inside this circuit. And we can use this now to calculate the current by combining this with Ohm's law. So this is the voltage induced inside the circuit, and all of that voltage has to be lost over this resistor. So we have that the voltage lost over a resistor is equal to the current flowing through the circuit times the resistance. This is my voltage. It's equal to BLV, so I can see the current flowing through the circuit is going to be equal to BLV divided by the resistance. And now what I can do is I can plug that formula into the formula for mass, and I can see that the mass of the rod is going to be equal to B squared L squared V divided by R times G. And if I plug these numbers into a calculator, I'll see that this is equal to 0.23 kilograms. And actually, it's probably worth just calculating the current as well, because I'm going to wind up needing that later on when I calculate the energy that's lost inside the resistor. So this current, if I plug these numbers into the calculator, so this is 0.5 Tesla, 1.3 meters, I think it was following at 4 meters per second, and it was 0.75 ohms. So if I plug these numbers in, I'll see that the current is equal to 3.47 amps. So we'll need that a little bit later as well. So here we've been able to find the mass of the rod. So part B is relatively straightforward. The change in the gravitational potential energy during the first 0.2 seconds, well, that's just going to be equal to the mass of the rod times G times the change in the height of the rod. And the change in the height of the rod is just going to equal to the speed that it's moving times delta t. I'll technically minus this because the rod is falling down. And if we plug all these numbers into a calculator, so our mass we just found was 0.23 kilograms, G is 9.8, V was 4 meters per second, and delta T is 0.2 seconds. So if we plug this into a calculator, we're going to see that the gravitational potential energy has decreased by 1.8 joules. So the last part, I want to now calculate the amount of energy that's lost inside the resistor in the top part of the circuit. And basically what we're going to find is that that energy is equal to the change in the gravitational potential energy. So what happened is that the gravitational potential energy of this rod was converted into electrostatic potential energy, and then that electrostatic potential energy was lost in the resistor, and that was converted into heat. So remember that the rate that energy is lost inside a resistor is given by this formula here. It's equal to I times V. And since I know the current that's flowing through my resistor, that's 3.47 amps, I should use the formula I squared times R. So what I did here is I plugged in V is equal to I times R, and then I get this formula for the power lost inside a circuit. Now, this is the rate that energy is lost in the circuit, so the energy that's lost during 0.2 seconds is equal to the power dissipated in the resistor times delta T. So if I take this and multiply it by 0.2 seconds, so we have I squared R times delta T. If I plug those numbers into a calculator, I'm going to see that the energy that was lost inside this resistor is equal to 1.8 joules. So you should double check these calculations, even plug them into a calculator if you're not convinced. You'll see that these two energies are actually going to be equal. So we're seeing conservation of energy between two very different types of energy, this gravitational energy and then this energy that's stored inside a circuit. And at this point, I think I'm going to end our discussion on electromagnetic induction, and I think when we come back next, we're going to be talking about waves.